Okay, so now we move on to continuous random variables. So we've covered the 5 discrete random variables that we need from 309, and now we're going to move on to the 4 continuous random variables. So just to draw a quick refresher on continuous random variables and the distinction between them and discrete random variables. So if x is a random variable and it's continuous if its range is continuous or uncountable. So if we're counting, for example, the length of time or the length of an interval, this is continuous or uncountable. And rather than the PMF for discrete random variables, it's defined by a PDF or probability density function fx of x. And unlike this summing to 1, this has to integrate to 1. So you kind of more or less replace sums with integrals, and that's what happens for the expectation and the variance calculations. We're not going to be using these calculations explicitly a lot today, but I just wanted to kind of go over those definitions. So now recalling that we're covering important important continuous random variables. So in particular, the first one we're going to cover is exponential. So remember that this was the waiting time until the first event. So we have, once again, this is just defined by one parameter, which is the rate at which events occur, which is lambda. And so what's the range going to be here? So the range can be any length of time. So it could be, if the event occurs straight away, it could be really close to 0. Otherwise, if we're waiting forever, it could be infinity. The PDF here is given by this formula. So it's lambda e to the negative lambda x. If possible, it's good if you can kind of draw what the PDF looks like here, and it's a decaying exponential. So it integrates to 1, which is important, and kind of the rate of decay gets bigger as lambda grows. And then in terms of the expectation and the variance, the expectation of x is 1 over lambda. You can calculate this pretty easily by integration. But once again, I like to think of this intuitively. I mean, the rate of events occurring is lambda, so the expectation of how long it will take for an event to occur is going to be the reciprocal of that, 1 over lambda. And so the exponential has a lot of sort of relationships with the geometric distribution in the discrete cases. The geometric is the number of failures until the first success, and this is really the amount of time until the first success or event. Okay, and the other cool thing about the exponential, which is unique, is that exponential, you can do this calculation, is memoryless. And it's in fact the only continuous distribution that's memoryless, and in fact the only discrete distribution that's memoryless is the geometric. And what that basically means is that if you've already waited time t for an event to occur, the chance that you'll be waiting another length of time s doesn't depend on the past. So it's another way to think about it is if x is modeling lifetime, if you've already lived for 50 years, the chance that you'll live another 50 years is the same as if you're just born, and the chance that you'll live another 50 years beyond that. So it may not be super realistic for lifetime, but that's a nice property of the exponential distribution. And so the final distribution associated with the point process that we're going to cover is the gamma distribution. And this is the waiting time until R events occur. And so we have two parameters. So the gamma can be thought of as an analog to the negative binomial in the discrete case, just like the exponential is like the is analogous to the geometric in the discrete case. And so once again, the range here is 0 to infinity. Once again, we have this this nice property that if we have R independent exponentials, then the sum of these R's is going to be gamma. Okay, and so this again is fairly intuitive, but another kind of nice property that's useful for calculations. The PDF, it's not super important that you remember it. Once again, we're going to use it. We're going to have it sort of written down, and but you know, just so that you've sort of seen it, I'm just going to write it down. And then the expectation, using the fact that we have sums of independent exponentials, the expectation is just going to kind of like multiply everything by R, as is the variance, because of the fact that we have sums of independent exponentials here. So the next and second last distribution that we're going to see today is the uniform distribution. So this is just the flat distribution over a fixed interval. So this is really defined as much by its shape as anything else. So its PDF basically just looks like a flat line between 2 points, A and B. So it has you know, two parameters, A and B. The range, as you can well guess, is just A to B, where B has to be bigger than A. I mean, whether the brackets are closed or open isn't super important here. The PDF here is just a flat line, so it's just going to be 1 over B minus A to ensure that everything integrates to 1. The expectation is just the midpoint of the range, is if we have a flat distribution, so if the average or the expectation is the midpoint. And the variance, which again you can calculate, is just given by this formula. There's a lot of nice properties of the uniform, but probably one of the most sort of interesting and a little surprising is that okay, so Yeah, this is a property that's very useful for a simulation. So the CDF is another kind of nice, way to characterize continuous or any random variable, which is just the probability that x is less than or equal to x. And so for any continuous random variable, actually, if you apply the CDF as a functional transformation to the random variable x, as long as it's the same CDF as x, you end up with a standard uniform, so uniform 0, 1. And this is extremely useful for probability simulations because it allows you to simulate any random variable just by taking a uniform and then applying the inverse CDF to it. Okay, so and part of the reason I'm giving you these properties is because I just want to give you some idea of why these distributions are actually sort of useful. And also, if I just list sort of, well, this is the expectation, this is the variance, the PDF, it's sort of not likely to resonate. But by giving these properties, it sort of tells more of a story about why they're interesting, or at least in my mind they do. So the final and most important distribution, I would say, in sort of all of probability and statistics is the normal distribution. We're gonna see this like almost every lecture in the course because it just comes up so frequently. So things like the central limit theorem, which we're gonna see in the next lecture, follows is characterized by this normal distribution. And so first, I'm just going to state that there's two parameters. So mu is the mean, and sigma squared is the variance. Okay, and so that should be sigma squared. So what it basically looks like is just a it's a bell-shaped curve that's centered at mu, and the width of that curve is defined by sigma. So the PDF, and this is not especially useful as a formula, but I'll state it anyway, because what we're going to see is that the normal has a lot of really cool properties, and using those properties is going to be much more important than using the formula. So what it looks like is just an exponential to the power of negative squared. So that's what really defines the normal distribution. So it's different from the exponential, because the exponential doesn't have a squared in there. That's kind of what makes this normal distribution special. The range here is just negative infinity to infinity, so it includes the whole real line. And what is not surprising is that the expectation is mu, because that's kind of how we've defined the parameter, and the variance here is sigma squared. Okay, and then what we referred to in the previous lecture, and what we'll often refer to as the standard normal, z normal 0, 1. The reason why we often refer to standard normal is that you can transform any normal to a standard normal through the following transformation. So we can say that x equals mu plus sigma z to get x from z. So if we wanted to get a normal mu sigma squared, we would just multiply z by sigma and then add a mu. And then conversely, you can say that z equals x minus mu over sigma. And this is a process that we often go through, which is just standardization or normalization. And often, if you're using like a z table or something like that, you'll first sort of subtract off the mean and divide by the standard deviation or variance. And that's because we can do this for the normal random variable. So the last thing I'm going to talk about today, and something that we're going to use throughout this course, is one of the reasons why normals are kind of so widely used and so cool, is that the normal distribution has a number of key properties, and so probably the most important is that okay, so key property is that the normal distribution is closed under the operation of linear combination. So if you take a linear combination of two normals that are independent, you get another normal random variable. And this is kind of really cool and really useful, and we're going to see that in action today. And that's why you can also standardize a normal random variable. So if you take x as normal mu x sigma x squared and y as normal mu y sigma y squared, if you take a linear combination, so if a and b are any constants here, so a and b are just any constants, then this is also going to be a normal random variable where the means are just a mu x plus b mu y, and the variances are a squared sigma x squared plus b squared sigma y squared. We're going to finish today with an example, and this is also a lead into what we're going to cover in the next lecture. Okay, so we're going to finish with this question, and I'd say that this is probably, it's getting to the end of the lecture, but this is probably the most important part of the lecture, so really pay attention to this, because a lot of the calculations I go through will be calculations that will be repeated numerous times throughout the course, and in fact were actually gone through were actually covered in the previous lecture as well. So here we have n independent normal random variables, and what we're going to do is take what's called a sample mean, which is the average of those n independent random variables. So we take 1 over n summation xi. So the sample mean is something that will be coming up pretty shortly, and we want to find, and part A asks us to find the expectation of x bar and the variance of x bar, and then part B asks us to see if we can find the distribution of x bar. Okay, so once again, I kind of encourage you guys to follow these calculations carefully and make sure you understand them. And if there's something that you're not sure about, sort of talk to me or refer back to your notes in 309. So let's to first work out the expectation of x bar. We can write this as the expectation of 1 over n times the sum of xi. So the expectation is linear. So another thing you'll potentially notice is that I've done today and in previous lectures is that I've kind of done operations with things like expectations and variances that, potentially like they were covered in hopefully in good detail in 309. And I've kind of assumed that you can do that. If some of these steps are not clear to you, I encourage you to go back to your notes and just also maybe email me, because these steps of, taking the expectation inside the sum and so on that I'm doing here should become natural to you, because we're going to use that quite quickly, we're going to use that quite frequently, and I'll just assume that that's known. So here, because of the linearity of expectation, we have that the expectation of x bar is just 1 over n times the e times the sum of these xi's, and so each of these xi's has mean mu, and so we just get that the overall expectation of x bar is mu. One thing to note is that we do not need an independence for this calculation. Now to calculate the variance, once again, we'll be using various properties of variance here. One thing to note is when we bring the variance, when we bring a constant out of the variance, it gets squared. And so that actually, as we'll see, will be really important. And that's one of the key reasons actually why statistics is actually useful, and we'll see this calculation come out throughout. And then the next question is, can we bring the variance inside? And in general, the answer to that is no. But in this special case, we can, because of independence. So we can bring the variance inside a sum when we have independent random variables. So in general, if your x's are dependent, you can't do this, but because we have independence, we can do this. So we're adding up the sigma squares, and so what we get at the end of the day is sigma squared over n. So we have that e of x bar is mu, variance of x bar is sigma squared over n. And that n is really, really important here, and understanding why that comes about is something that you should be becoming pretty comfortable with. And one thing to note here is that we have not used normality or the fact that the x's are normal at all here. This is where we're going to exploit it for part B. So we want to find and this is where we can say that by property of normal, since we have a bunch of independent normals and all we're doing is taking a linear combination of them. Sorry, let me just write this properly. Then, we're taking a linear combination is also going to be normal. So this is not going to be true if the xi's did not follow a normal distribution. So x bar is clearly going to be normal, and then all we need to know is the normal is just defined by its mean and its variance. So So we have that x bar is normal with some expectation and some variance, and we've already calculated what that expectation and variance is. And so we get that the mean has the same expectation as each of these xi's, but importantly, the variance is much smaller. So we get a lot more concentration around the mean because the variance shrinks by this factor of n. And so that's kind of that's a really kind of important property that we're going to use throughout. So to summarize, that's all the material that we'll cover today. So there are 9 distributions that we've learned about, and I kind of went through them extremely quickly. Be comfortable with those 9 distributions, and in particular, the best way to be comfortable with them is to sort of know where they arise and when to use each one. And then, that last example that I did with the normal, I would say just go through that carefully and make sure that you're pretty comfortable with that. Okay, so thanks for listening today, and I'll be posting the next couple of lectures at the beginning of next week. Okay, thanks very much. Bye.